Okay, guys, so last time in chapter 20, we did explain that carbonyls, they do undergo a process which is called rearrangement. Rearrangement is tautomerization, so this is the same idea, where you go from a keto form to an enol form. And we said that the keto form is more stable at equilibrium. This is what we said. The enol form is simply whenever the double bond rearranges or the double bond just shifts to the adjacent carbon, okay? And one of the hydrogens of the alpha carbon, they rearrange to the oxygen. This is what the enol. We say that the enol is unstable because you do have oxygen OH, which is a nucleophile, which is next to a double bond, which is a nucleophile. This is why we say it's not stable and it exists in less than 1%. Enol forms, they depend on the number of alpha hydrogens that you have. Here I do have one alpha hydrogen because it's a symmetrical ketone. So this is why I have one enol form. If you have two alpha hydrogens, then you're going to end up getting two enol forms. And still the enol forms, no matter how many they are going to be less than 1%. We said that the enol form and the keto form, these are tautomers, which is constitutional isomers of each other. Now, before you pass to the enol form, you need to pass by an intermediate, which is the enolate. Why is that? Because we said that you look always at the alpha hydrogen, and this is the process. You have a base, and the base comes and takes that alpha hydrogen and create the enolate. Once you get the enolate, and this is what happens to get to the enol, these are the steps. It's simply by resonance in there with a negative charge. The oxygen will carry a negative charge, and then you're going to have a hydrogen added. Just add a hydrogen, and the hydrogen comes from any solvent that has a hydrogen, and you simply get your enol. So the point is, to get from a ketone to the enol, you need to pass by the enolate. Okay? So this is the whole idea in this chapter. Making the enolate. Once you make the enolate is going to serve as a nucleophile, period. This is the whole idea. So it can add to any partial positive carbon. So the nucleophile is going to add to any positive or partial positive carbon in there by a reaction between a nucleophile and an electrophile. Simple reaction in there. Okay? So in these reactions, the reactants are going to be in excess. We have a couple of reactions, and each reaction has a name. This is why in each of the problem sets that I gave you, I have the name of the reaction in there for every single problem set for more practice. You don't have to do them all, but do as much as you can. So with the aldol condensation, the reason why it's called an aldol, because it's a reaction between either two aldehydes. See, it's in excess. So whenever you have an aldehyde, this means that the aldehyde is always in excess. Or two ketones that are the same. Okay? So it's either two aldehydes or two ketones. If you look at the problem set, the first problem set, if you see an aldehyde, always the aldehydes are in excess. Always the ketones are in excess. So with these, please treat all the reagents in excess. This means that you are going to react them twice in there. Okay? So the idea here is we're going to form the enolate from one aldehyde and then use another aldehyde and react it with that enolate in order to get our product. This is the whole idea in there. So always you create the enolate. The reaction goes in a basic medium, and the bases that we use. The best base for the aldol condensation is the sodium hydroxide. You're going to see it a lot. And the solvent is water. If you use sodium alkoxide, like an O-methyl or an O-ethyl, normally with that, we use water or we use methanol. Methanol or ethanol, it depends on the R that you are working with. So if the R is an ethyl group, then you use ethanol. If the R is a methyl group, you use methanol. But normally with sodium alkoxide, the best solvent is not water, it is an alcohol. Sodium hydroxide is used best with aldol condensation, but I can also use NaOR, and the reaction proceeds the same. So this is the reaction, okay? The product is going to be very big because you are condensing. It's called condensation because you are bringing together two aldehydes. So the product is going to be a big molecule in there, and it's going to have the same number of carbons as the aldehyde that you start with multiplied by 2. So here I do have 2 carbons, so this means my product is going to be 4. The reaction is going to go by a base in presence of water, the sodium hydroxide in presence of the water in there. And always you use excess. If I say 2 or if I don't say 2, it's always in excess. Okay? So again, you're going to create an enolate from the first aldehyde, and then you're going to use that enolate to react it with the second aldehyde. The reaction proceeds by a base, and that base is going to come. So you have your base. That base is going to come and take always the alpha hydrogen. Now, if you will rarely have a compound that has more than one alpha hydrogen, okay? I'll make sure about that. But if you have a compound that has more than one alpha hydrogen, this means that you're going to go both routes. So you're going to end up getting 2 products in this case. So the base is going to come, take the alpha hydrogen, and again, the alpha hydrogen is the hydrogen which is next to the carbonyl. We call this an alpha carbon, and it's all its hydrogens are alpha hydrogens. So the base is going to come, take the alpha hydrogen and form the enolate. This is the first step. Now the second step, I'm going to use that same aldehyde, and see, I make it easy on myself and I put them underneath each other, so that because I want to form a bond between the carbon of the enolate, I want to form a bond between this carbon here and this carbonyl there. So just make it easy and put them on top of each other in there, so that you would know that there will be a bond between this carbon and this carbon there. So the enolate is going to come and attack the carbon of the negative charge. Is going to come and attack now the carbonyl. So here the reaction is basically 2 things going on. Base taking the alpha hydrogen, so you have an acid-base reaction. You make your enolate, which is the conjugate base. Once you make your enolate, the enolate is going to act as a nucleophile now and attack the carbonyl. It's not going to act as a base. It's going to act as a nucleophile, attack the carbonyl, form a negative charge on the oxygen. So see what I did over here? I created a new bond in there between the 2 aldehydes. The aldehyde that has the carbonyl, this comes from the enolate. This is the enolate. And the aldehyde that has the bond O negative, this comes from the second aldehyde in there. You are not going to synthesize those. So I'm not going to give you the product and ask you make it. Okay? So there is no synthesis for these reactions. All I want you to do is know the process of the reaction. Now, once you have this, definitely now you're going to use your solvent to pick a hydrogen for the oxygen, and you're always going to get for these reactions your first product, which is the alpha beta or the beta hydroxy and whatever aldehyde or ketone you have in there. Here I do have an aldehyde, so this is why I'm going to call this beta hydroxy aldehyde. Okay? Now, the reaction doesn't stop here, but you will always form the beta hydroxy aldehyde, but the reaction cannot stop here because if your medium is basic, the base is going to continue to react. So you have to pay attention to that. And once you form the beta hydroxy aldehyde, the steps are always the same because the base is going to react now by elimination. The type of elimination that I am working with here, I'm going to call it an E1. It's a CB. CB means a beta carbon. It's a beta carbon. This is E1CB. It's an E1 elimination on the beta carbon. So if you can see here, This is not a regular elimination. This is not a regular E1 because I know that OH is a bad leaving group. And to eliminate the OH, I need to protonate, but I have nothing here to protonate the OH. This is why this type of elimination is different than the E1. We call it E1 elimination at the beta carbon. What does that mean? It's a reaction that occurs under basic conditions where you remove a hydrogen from the alpha carbon, and this hydrogen from the alpha carbon is normally relatively acidic, while the leaving group is a very bad base. It's a strong base, which is a bad leaving group. And this is why I'm calling it E1CB, which is the elimination at the beta carbon. The OH still leaves. The OH still leaves in there. And why it leaves? Because you normally make your enolate, and the enolate forces the OH to leave. So this is what happens in there. The base is gonna come, and again, the base here, because you are using a basic medium, so the base is gonna keep reacting in there until elimination forms at the end. These are the two steps of the E1CB. Normally, we won't repeat those steps every single time, but every time I say E1CB, this means that these two steps are gonna form. The OH minus is gonna come, take the hydrogen, form the enolate. This is the first step. And the second step, the enolate is going to force the OH to leave. This means it's as if I'm losing water. And the water is going to come from the alpha hydrogen and the beta OH. So with E1CB, it's as if you are losing an alpha hydrogen and a beta OH. And your final product is going always to be an alpha beta unsaturated. This is an alpha beta unsaturated carbonyl, whether it's an aldehyde or ketone. So always go to the end. Always, whenever you are doing the elimination for aldol condensation, your final product is always going to be the alpha beta unsaturated aldehyde. You're going to pass by the beta hydroxy, but do the E1CB elimination, take the alpha hydrogen, take the beta OH. You don't have to show the steps, just say E1CB minus alpha hydrogen minus beta OH and go directly from this here to the final product. And this is actually what I'm showing every single time. I'm not showing those two steps in there. So the overall reaction, this is how it's going to occur. It's either like I would mention that the aldehyde is in excess, but sometimes you won't see any two in there. You're just going to see the aldehyde. You're going to see base and presence of water. This means that the aldehyde is in excess and the base is in excess. You're going to continue your reaction all the way until you form the alpha beta unsaturated aldehyde. Let's have another example. So in all of these, I'm making sure that we only have one alpha hydrogen. So on this carbon, there is no alpha hydrogen, but on this one there is. So there is an alpha carbon in there with alpha hydrogens. This is the acetophenone, so I'm going to use it twice in there, and this is how it's going to be, same steps. Base is going to come, attack the alpha hydrogen, make the enolate. Once you make the enolate, please put them under each other. Get another molecule of the ketone that you are working with, and the enolate is going to come, attack the carbon of the carbonyl, form a negative charge on the oxygen. Once you do this, just make sure that to count the carbons, because the carbons are going to be always double, okay? So here I made a bond between this carbon here and this carbonyl over there. And this is actually the bond, the new bond that I made. And then we said that the part here comes always from the enolate, and this part over here, which is the O negative, comes from the second attack of the second aldehyde. You always make a bond, a new bond. And then next step is the protonation of the oxygen. The steps are exactly the same. And you're going to end up forming the beta hydroxy. In this case, it's going to be a ketone. After you form the beta hydroxy ketone, please do the E1CB always. The elimination, E1CB, proceeds by two steps, but you don't have to show the steps as up there every single time. Just do the same as I am doing, minus the alpha hydrogen. And the alpha is the carbon that is next to the carbonyl. This is how you name it. This is an alpha carbon. This is a beta carbon. The carbon next to it is going to be the gamma carbon and then the delta carbon. But we're not going to be dealing with those. We're going to be only dealing with the alpha and the beta. So you take the alpha hydrogen, the beta OH, and you form an alkene in between. Your product is always going to be an alpha beta. Unsaturated means a double bond between the alpha and the beta. And then here it is a ketone. The reactants can be any aldehyde, any ketone in there. So it's like a lot of examples you can come up with. Any aldehyde, any ketone, as long as the aldehyde has the alpha hydrogen. So this one has an alpha hydrogen here. So starting with the base, taking the alpha hydrogen, making the enolate. And the enolate is going to attack the carbon of the carbonyl. The reaction is really simple. Forming a negative charge on the oxygen, you protonate. Here I am using ethanol as a solvent. So I'm going to use the ethanol here to protonate the oxygen and make it an OH. So your product is always going to be, before the alkene, it's going to be the beta hydroxy. And here it is an aldehyde. After you do this, do the E1CB always, because your medium is always basic. You're forming your enolate, and then you're going to do the elimination, and you're going to get your alpha beta hydroxy or alpha beta unsaturated aldehyde in this case. This is your alpha carbon. This is your beta carbon. You take out the alpha hydrogen. You take out the beta OH, and you make your alkene. Okay, another example, this is a ketone. This is a symmetrical ketone here. So you will have basically one type of alpha hydrogen. So here you do have an alpha hydrogen there. Okay, so you have one type of alpha hydrogen here because it's a symmetrical ketone. So the base is going to come and take the alpha hydrogen, make the enolate, use another mole of the ketone, form a negative charge. Every time you form a bond, you break a bond. Please remember this, okay? And then with the solvent, you protonate, you form the beta hydroxy ketone, and then do the E1CB and get the alpha beta unsaturated ketone. Any questions on this reaction? Okay, it's a very simple one, and I did give you a lot of examples. Most of these examples are in the problem set in there. Again, this is now with sodium ethoxide, NaO ethyl. ET is an ethyl group, please. Okay, ET, this is an ethyl group. You all know this by now. This is an ethyl group in there. So you start with the base, form the enolate. The enolate is attacking the carbon, but honestly, you won't master it unless you write the mechanism down, okay? So please write it down. Not just look at it, write it down at home. Form a negative charge on the oxygen, and then this negative charge is going to get protonated by the solvent in there. So this is going to get protonated by the solvent. O-ethyl is going to leave. And there, see, your base is always there. So this is why your medium is always basic. The base comes from whatever, from the solvent, whatever leaves from the solvent, and from the actual base itself. So this is why E1CB always happens in there, and you get your alpha, beta, unsaturated ketone. That is for the aldol condensation. Look, you guys, the reaction is always the same. It's just the name of the reaction. I'm changing it because the reactants are different, but the reaction is still the same. So instead of mixing two aldehydes that are the same or two ketones that are the same, I'm just going to mix an aldehyde and ketone together. And that is going to be called mixed or crossed, and we're still in aldol condensation. So mixed or crossed means that I'm mixing two different aldehydes, two different ketones, meaning that the aldehydes and ketones are not the same, or I'm mixing an aldehyde or a ketone, or I'm mixing an aldehyde or a ketone with a diester. In this case, this is called mixed aldol condensation. Reaction is always the same. Medium is always basic. And please remember that if you are to choose between the alpha hydrogen of the aldehyde and the alpha hydrogen of the ketone, always the alpha hydrogen of the aldehyde is more acidic. So you go with that. You always go with that, okay? And the reaction goes like this. So you start with whatever carbonyl, and it's 2 steps or maybe more. It depends on the reagents that you are adding. So you have your base, this is the first step, and then in your second step, this is another aldehyde. So you can see here that I have another aldehyde. Now here it's obvious that this aldehyde is reacted first with the base. And then you add that second aldehyde. Is that clear for everybody? Okay, so this aldehyde here should have an alpha hydrogen because it is reacted first, and the base needs to take the alpha hydrogen to make the enolate. Once it makes the enolate, then that enolate is gonna come attack the second aldehyde, the carbonyl of the second aldehyde, and there you can put them underneath each other. I didn't here. Form a negative charge on the oxygen, so nothing here, so everything is the same. And then that negative charge is going to get protonated with the solvent to form the beta hydroxy aldehyde. So you're always going to form the beta hydroxy carbonyl here. So beta hydroxy, here it's an aldehyde. With aldol, please you guys, always form the alpha beta unsaturated aldehyde as a product. Don't stop, because whenever you do the protonation, you're going to end up having an O-ethyl again in your solution. So see that O-ethyl in there in your solution. This is a base, and you already have a base, which is the OH minus in the solution. The solution is already basic. So that base is always going to come and take an alpha hydrogen and make an enolate. You do have an alpha hydrogen in there. So the base is going to come and is going to take an alpha hydrogen. So there is an alpha hydrogen. You make your enolate, and then the enolate is going to push by the E1CB the elimination, and the OH is going to leave, and you're going to get your alpha beta unsaturated aldehyde. Because you're getting an alkene, you will be getting isomers in there. You will be getting the cis and the trans. But the trans is always, or the E isomer is always the most stable one. Okay? So the E isomer is always the most stable one, and this is why I'm drawing the most stable isomer. I am neglecting the least stable one. But this doesn't mean that the least stable one does not form. It does form in like a very low percentage, like a 5%, 7%, but the majority is for the major isomer, which is the E isomer always. Another example, okay, so this is another example in there. Again, this is a mixed aldol because you have 2 different types of carbonyls in there. You create your enolate in one, you react it with the second one, you use your solvent, you form your beta hydroxy. This is the beta hydroxy ketone. And then you do the E1CB, always locate your alpha hydrogen, your beta OH, remove them out, and you get your isomer. Always form your E isomer, not the Z, the E isomer in there. Okay? More examples of crossed aldol condensation. The moment I start with an aldehyde, this is called an aldol condensation. If the aldehydes are the same, or if the ketones are the same, then it's going to be called simply aldol. If the aldehydes and ketones are different, then it's going to be called crossed or mixed aldol. And if the aldehyde is reacted with a diester, this is a diester in there. I've wrote it in its condensed form. This is its actual structural form in there. Okay, as you can see, this is a diester. It's a CH2, which is surrounded by the 2 groups of esters in there. The C double bond O, O-ethyl on one side, and another group similar to it on the other side. This is called diethyl malonate. You don't have to know the name. You don't have to know the name in there. This is the common. You don't have to know it, but of course you need to know the IUPAC. This is the diethyl ethanoate. Reaction is exactly the same. As you can see here, the difference here is that the aldehyde doesn't have the alpha hydrogen. Your alpha hydrogen here it comes from the diester, which is the most acidic alpha hydrogen here. This is the most acidic alpha hydrogen because it's between two carbonyls. So let's say even if your aldehyde has an alpha hydrogen, this is a more acidic alpha hydrogen. Okay, so this is why the base is going to come and take this more acidic alpha hydrogen. So I'm just going to put this as a note that this is an acidic alpha hydrogen, and it is more acidic than if the aldehyde has an alpha hydrogen. I said if because here the aldehyde does not have an alpha hydrogen. It doesn't have an alpha carbon, but on this carbon there is no alpha hydrogen in there. Okay, this is a benzene, and the carbon already has a 3 or 4 bonds in there, so no alpha hydrogen. One more thing, this is not an alpha hydrogen. So this is not alpha hydrogen. It is not acidic. This is a simple hydrogen of the aldehyde. We said this belongs to the sp2 hybrid carbon, and it's very hard to break the bond between the sp2 carbon and the hydrogen. So this here, the base can never take it. But again, if your aldehyde has an alpha hydrogen, the diethyl melanate has the alpha hydrogen, please take the alpha hydrogen between two carbonyls. It's way more acidic than the alpha hydrogen of the aldehyde. So the base is going to come, take the alpha hydrogen, make the enolate, and then now the enolate is going to attack the carbonyl of the aldehyde. Do exactly the same steps. Since it's an aldol condensation, it should end in E1CB. So you're going to form your ethanol. You're always going to get your beta hydroxy, but here in this case, it's going to be a diester. And then the E1CB happens always with aldol, because the medium is basic. In this case, you're going to take the alpha hydrogen. We're going to take out the beta OH. This means that you're taking out water, and your product is going to be the alpha beta unsaturated. Here in this case, it's a diester. You're going to get the alpha beta unsaturated diester. You guys, this reaction can continue. If I use more reagents, it can continue. Now, with these reagents here, with the NaOethyl and ethanol, it's going to stop here. So this is going to be your final product, okay? But let's say, for example, if I continue and use H3O+. So if I continue, take this one and use H3O+ in there, okay? So I took this here and I continued the reaction. So with H3O+, we all know that this is ester hydrolysis in acidic medium. So both esters are going to turn into a carboxylic acid. So both esters here are going to turn into a carboxylic acid. And then if you do heat, you simply eliminate carbon dioxide, because I do have a condition here where I do have two carbonyls separated by one carbon, and this is the carbon. And one of the carbonyls is a carboxylic acid. So I'm going to lose carbon dioxide here. Okay, this hydrogen will be added to this carbon, and I'm going to end up getting my final product. So I can add reagents to this reaction, and this is how it's going to look like. So after I do the aldol condensation, I do H3O+, and then I do heat, and I'm going to end up getting my final product in there. Okay. Let's have another example. So see here, you do have, I give you an example where the aldehyde has the alpha hydrogen, and the diethyl ethanoate also has alpha hydrogen. But the alpha hydrogen here are more acidic. They are more acidic. They are more acidic because they belong to two carbonyls. So this is why the base is going to come, take the alpha hydrogen from the diethyl melanate, form a negative charge. This is your enolate. and that is going to come attack the carbon of the carbonyl, form a negative charge on the oxygen. With ethanol, you're going to end up getting your beta hydroxy. This is going to be a diester, okay? And then you always have to do E1CB with aldol condensation, and you're going to end up getting your alpha beta unsaturated. This is alpha beta unsaturated diester. How do you know you're doing E1CB? Every time you start with an aldehyde or a ketone, this is going to be aldol condensation. So if the aldehydes and ketones are not the same, then this is going to be a crossed aldol condensation. So always with the aldol condensation, you're doing the E1CB, the last step in there. You get your alpha beta, but here we have more reagents with H3O plus and heat. So please continue with the ester and hydrolyze both esters into carboxylic acid. Take out one carbon dioxide, just one carbon dioxide, and get your final product. Okay? We're still in the aldol condensation, but we can have two aldehydes in the same molecule. Aldol reactions, you have your aldehydes or ketones in the same molecule. So I do have two carbonyls in there, okay? In the same molecule, still the same reagents, base, and presence of a solvent. Now, here's the thing. The alpha hydrogen that you're going to choose, because you're going to end up having more than one alpha hydrogen based on the carbonyl in there, because both sides of the carbonyl might have an alpha hydrogen, whether it's this carbonyl here or this carbonyl there. Now, it happens that the first one is symmetrical. These two carbonyls are basically symmetrical because both they have a CH3 and both they are surrounded with CH2. So this is a symmetrical carbonyl in there. But let's say if it is not symmetrical. The alpha hydrogen that you're going to choose, you want to make sure that the alpha hydrogen makes the most carbon cycle as you can form, up to 6 carbons. Because after all, you're going to make your enolate, and that enolate is going to attack the second carbonyl. So you want to make sure that the cycle that you're forming is at most 6 carbons. If you have the choice between 5 carbons and 6 carbons, you choose the 6 carbon cycle because it is more stable. The more the carbons are farther away from each other, the less the angle strain of the cycle and the more stable is the cycle. This is why I went with the alpha and I didn't go with the alpha prime. Because if I go with the alpha and there is going to create an enolate, see, the enolate that is going to create here, it's going to be on this carbon. And then if that carbon, this enolate, is going to come and attack the second carbonyl, I'm going to form a cycle of 5 carbons in there, versus if I create or if I let the base attack the alpha prime hydrogen, then in this case, let's go ahead and number the carbons. There's going to be 1, 2, and 3. Then this is going to come and attack the carbon of the carbonyl and make a cycle of 3-membered rings. Do you see that? See the difference in there? Okay. So this is why go with this one over there. Go with the alpha hydrogen. Create your enolate. And then allow the enolate, same steps, but here the aldehydes are, or the carbonyls are in the same molecule. So if they are in the same molecule, you will be forced to make a cycle, but please number your carbons starting from the enolate towards the carbonyl. So here I'm making a bond between carbon 1 and carbon 5. When you number, just to draw the carbon cycle number that you formed. So you have 5 carbons here cycle. Just to draw first the 5 carbon cycle. Draw it. After you draw the 5 carbon cycle in there, just number, I made a bond between carbon number 1 and carbon number 5. This is the new bond that I made over here. This is the new bond. Okay? So go ahead and number carbons 1 and carbon 5, and then number the carbons in between. After you do this, just go ahead and put the substituents on the carbon. So I have on 5 a CH3, just go ahead and put a CH3 in there. On 5 you have the O negative, put the O negative in there. On 2 you have a carbonyl, put the carbonyl in there. Then go ahead and protonate with the solvent and then do the E1CB since we're still doing the aldol condensation. Take out the alpha hydrogen. take out the beta OH, and you get the alpha beta unsaturated ketone. So you're always going to form the beta hydroxy ketone, do the E1CB with the aldol, and get the alpha beta unsaturated ketone. Another example of the intramolecular aldol condensation. Again, two carbonyls here. I do have an aldehyde. I do have a ketone. Now here, I'm not going to go with the most acidic hydrogen, because I know that the alpha hydrogen of the aldehyde is more acidic than that of the ketone. But what drives this reaction is more carbon cycle. Okay, so please put this as a note for here. What drives the reaction is forming more carbons in a cycle up to 6 carbons. You cannot form 7 carbon cycles. So let's go ahead and see over here. So do not go with the most acidic alpha hydrogen. See, if I went with the most acidic alpha hydrogen of the aldehyde, that will form a 4-membered ring. On the other hand, if I went with the less acidic alpha hydrogen of the ketone, then that is going to form a 6-membered ring. 6-membered ring is more stable because it is less angle strain. And always our product should be the most stable product in there. So the base is going to come, take this alpha hydrogen, form the enolate. Please number as I am doing in there. I'm forming a bond between carbon 1 and carbon 6 to draw the cycle of the 6-membered ring in there. Form a bond between carbon 1 and carbon 6. And then form the negative charge, protonate, do the E1CB, and you get the alpha beta unsaturated ketone.